So in the last class, we talked about atomic operation. Sorry, we talked about semaphores in the last class. And hopefully at this point you have a pretty good idea of what a semaphore is. Conceptually, you understand the APIs that Java provides to do semaphore access, to acquire and release the semaphore. Have you seen some examples, hopefully, at this point? And now we're going to talk about another synchronization class, or a class of synchronization capabilities, which are these atomic classes and operations. And the first thing I'll do is give you a quick overview of the Java memory model, because it's helpful to understand the next part. And then I'll talk about how these atomic operations allow concurrent programs to use so-called lock-free, thread-safe mechanisms to read and write to single variables. So that's what the atomics do. So first, just a quick summary of the Java memory model. If you are really bored or you're having a hard time falling asleep, go ahead and take a look at the Java memory model document. It's here. That's actually the FAQ. You can also find the memory model online as well. And what the memory model does is it basically defines the semantics of Java programs in general, and the part we care about are the semantics of Java programs with respect to multi-threaded access to shared memory. So keep in mind, in a modern multiprocessor, multi-core system, you'll have a bunch of threads which are mapped to cores, and those threads have cached memory that they can access, and that cached memory is ultimately backed by main memory, which is sort of ground truth. And the tricky part here is to figure out how the caches should be updated and flushed and so on in order to be able to give you the sensible behavior of your program. And the general rule of thumb is if you don't use synchronizers properly, then anything goes, or almost anything goes, and I'll talk about what anything means in this context. So you need to make sure you use synchronizers. So one of the things that Java memory model defines is what instruction reorderings are allowed in memory. So first of all, what the heck does it mean to reorder stuff, right? What does that mean when you talk about memory ordering, or linearization is the other way to look at it? What does it mean to be able to execute instructions out of order? Does anybody know? So what it means is that modern multiprocessors, for a variety of reasons, can actually allow reads and write operations to pass each other in memory so that the order in which they're executed in the hardware differs from the order in which you see them in your program. And I'll give you an example of that using this code here, this pseudocode, in a second. There's a whole bunch of places in a program that can reorder instructions. The compiler can reorder stuff to optimize things. The just-in-time compiler can do it. The processor caches can do it. All kinds of things can do it. You know, the hardware, the things do speculative computation. There's all kinds of things that can happen to reorder stuff. So let's take a look at an example. So here we have some variables, x and y, and let's assume, for sake of argument, that they're visible to thread 1 and thread 2. And we start out by setting them to the value 0. So x and y start out with 0. And then over here in thread 1, it sets x to 1, and then it reads the value of y. So this comes first, followed by that. And thread 2 sets the value of y to 1, and then it reads the value of x. And the question is, as time progresses downwards from top to bottom, where top is the instruction that occurred first in a lexical reading of the program, what's the order in which these operations are actually performed, and how are they reflected back into main memory, which is where ground truth resides, right? Because the other things are just cached. So it actually turns out that if you don't do anything to the contrary, you could end up with I equals 0 in this thread, and j equals 0 in that thread. And that's because there's nothing, the Java memory model doesn't stop things from being reordered such that this operation here, I equal x, runs without seeing the change of x equal 1, even though x equal 1 appears, in quotes, to have appeared earlier. Right? It just so happens that the way that caching can work and reordering can work, it may turn out that we end up with both of these things being 0, even though the values were set to 1. Now, quick question. How do we prevent this from happening? What's the way to ensure that we get the right values? Synchronizers, that's the trick. Okay, so that's one thing. Another question is, what are the outputs that can occur in a virtual machine implementation or a Java execution or runtime environment implementation? What's the outputs that can show up, given the fact that the compiler and the runtime system and the hardware is free to reorder things unless you tell it otherwise? So, and again, you can read the spec to learn more about this. We want to be able to allow flexibility, but we don't want to have the system just randomly create values out of thin air. That's also considered bad. So here's an example where we have x equal y equals 0, and then in thread 1, r1 is set equal to x, and y is set equal to r1. So you would think that, y would be set equal to x here. But here's over in thread 2, we have r2 set equal to y and x equal to r2. And so once again, the questions here, when this thing is done, what are the values of r1 and r2? Can they just be random? Can they be anything that the system feels like? No, they actually have to have some sensible output. And the sensible output has to be essentially some linear sequence of operations. And that's kind of the way that the Java memory model is defined, which is a little bit more strict than is probably necessary, but it helped allow people to understand, to make sense and reason about their code. Now, it turns out that reading the Java memory model spec is really, really boring. So you can do it if you're having trouble falling asleep. But the key thing to remember is, as long as you apply Java synchronizers properly, then all these subtleties that the memory model is defining in order to be able to give lots of room for optimization really sort of go away. So the general rule of thumb is, don't access or don't try to read and write unprotected, shared mutable fields that are shared between multiple threads. Do not do that. And as long as you don't, sort of access these fields or write to these fields in a naked way, then you'll be fine. It's when you forget to put the synchronizers in, or you start trying to play tricks and cut corners and throw salt over your shoulder, or go consult a Ouija board or whatever to get some good luck. That's when things start to go awry. So the key thing is that you just need to understand how to use synchronizers and follow certain patterns, and then all is well. And most people who get into trouble are trying to cheat and trying to take advantage of aspects of the memory model that are not really defined to do that. Okay, so given that as background, let's talk about atomic classes. So there's a couple of different classes in the Java atomic package. We're going to focus on one of them in particular and do a deep dive into how it works. They're the atomic variables, which we're going to look at. And these provide the lock-free, thread-safe operations on single variables. We're going to look at that. In particular, we're going to focus on atomic long, which uses the compare and swap operations we talked about before. And there's also these other things called long adders, which are used to have eventual consistency for doing operations that are highly contended between multiple threads, but don't need the right value right away. So a good example would be incrementing a count in a multi-threaded web page or web server, where you just have to keep track of the number of times each page was accessed, but you don't really care at any instance what the specific value is. You just have to know by the time it's all done running what the values were, because maybe you're going to use that as part of your AdSense campaign to reward people who were clicked on more than others. So let's talk about atomic operations. I've mentioned this before. Atomic operations are implemented in hardware and often have some support at the OS and middleware layers. If you take a look here, this is a website that Intel provides that talks about their atomic instructions that they provide on the x86 architecture, which is very common, so it's worthwhile knowing about this. The most important method is compare and swap. I'll show you the other one just briefly, and you'll see why compare and swap is better. So what is compare and swap? I gave you a definition before, but I'm going to really dig into it now and show you step by step exactly how it works. So compare and swap is an atomic operation built into the hardware that atomically compares the contents of a memory location and compares a given value, and you compare the memory location's value to something you basically expect it to be. So you say, is the memory location this thing? And if and only if they are the same, then it atomically modifies the contents of that location to a new value and returns the old value. Okay, so let's kind of that's the definition. Let's break it down and we'll see each piece. So the first point here is atomically. So the whole thing here is done atomically. So you can imagine, this is in pseudocode at this point, there's some kind of start atomic operation which is built into the hardware. This whole thing is built into the hardware, but if you were to look at the hardware implementation in the VHDL or whatever, you'd see that it starts the operation, does some stuff, and then it ends the operation. So all these things are guaranteed to run atomically. They either run or they don't run. And that, of course, is completely orthogonal to the issue of whether the processor is going to time slice away from this thread while it's running. Doesn't matter whether it does or not. This thing either all runs together or doesn't run at all at a given point in time. So it then compares the contents of a memory location to a given value. So as you can see here, we're going to get the old value, and then we're going to compare the old value at the memory location to the expected value. So you can see expected is one of the parameters passed in here. So there's a comparison that's done. And if and only if they match, right, if those two values are the same, then we update the memory location with the updated variable or updated parameter. We only do it if they match. And then the last thing we do is we return the old value. So the old value, which has been stashed away up here, is going to be returned as the result of the method. Okay, so that's what it's doing. And it's obviously very simple. And you can imagine building this logic into the hardware as a set of hardware instructions and gates and all those kinds of good things. Now, how do we use this? So again, this is kind of C-like code. So we're going to have a lock method. And the lock method is going to use compare and swap in order to implement mutual exclusion or a mutex using a spin lock, right? So not unlike what you're doing for your programming assignment. So here's what it does. It's going to use the compare and swap method, and compare and swap, as you recall, takes a memory location, right? So it takes the pointer to the mutex pointer. It's a pointer to a location in memory that stores an int. And it takes the mutex, which is what gets passed in up there, and it checks to see if the mutex's current value is 0. So is the current value equal to the expected value? And if it is 0, then it's going to atomically set the value to 1, right? So if it's 0, it's going to set that to 1. And what it's going to do is it's going to keep looping while the current value equals 1. So the way to read this is, while the current value of the memory location is 1, where 1 means it's not available, or 1 means it's locked, or 1 means it's busy, right? Whatever you want to call it. While it's busy, keep spinning. And only when it's not busy do you make it busy, right? So that's the compare and swap. If it's not busy, lock it. Or if it's unlocked, lock it. If it's not busy, make it be recorded as being busy. So that's basically how the logic works. Again, it's very, very simple. It's only complicated in the sense that it's low level. Yes, Xavier? So as you can see, it stashes the old value. So whatever the current value is of the location, it stores that. And then it does the check. And no matter what it does, it always returns the old value. So the way to look at it is, if the old value or the current value is 1 locked, it'll return 1. So that says, and in that case, if you're checking to see if it's 0, it'll return 1, which indicates to you that it wasn't unlocked. So you have to keep looping until it's locked, until you can lock it. And the key thing to remember is that the checking and the locking is atomic. Those things either happen or they don't. There's no in between. There's no race conditions, check then act race condition problem in this case. Now, how do we unlock this mutex? Well, that's simple. Atomically, we simply set the mutex equal to 0. We set the value of the location equal to 0. So all that's doing is that's just atomically setting this value so that next time it's checked, it'll be 0. So it'll be unlocked. So 0 means unlocked. Yes, Amanda? Okay, so let's take a look at this. So the question was, why do we have to loop? So the goal here is to lock, right? As the method name gives away, it's trying to lock something. So let's come in here and let's assume, for sake of argument, that the current value or the old value or the location value is 0. That's the unlock. Let's say it starts unlocked, right? So it starts out unlocked, starts out with 0. We come in here, we say compare and swap, 0, 1, as I think you just alluded to. The first thing it'll do is it'll atomically find it is 0, change it to 1, we're done. There was no need to loop for that case, right? So if the resource, if the mutex is unlocked, then there's no need to loop. What happens if somebody else owns it? What else happens if it's already locked, right? Then when we come in here, remember the current value will be 1. We're saying, I want to keep spinning until that value was 0, and then I'm going to lock it, right? So it's the reason we needed a loop is because if it's locked, we've got to keep spinning until it's available. And think about this in everyday life, right? This is very obvious. If you want to, use the restroom in the plane, then if it's unoccupied, you just go in and shut the door, right? You're done. If it's occupied, then what do? You stand there and you spin, right? You're sitting there spinning, logically spinning. I think if you spun, they would probably, the air marshal would arrest you because they think you were, on drugs or a terrorist or something like that. But be that as may, or either that or you're doing the art of, what is it, Ninjago, spinjitzu, that's it. You're doing spinjitzu if you're spinning. So basically, you only spin when it's locked because it's not, you're waiting for it to become unlocked. And that's why it's a spin lock, right? Because you don't go away until you get it. So you spin until it's locked, until it's unlocked and you lock it atomically. Did that answer your question? Okay. All right, so this atomically resets the value to 0. That's the key thing. It's this atomic operation. Okay. There's another operation called test and set, and this is a more traditional way of doing things. And test and set will automatically modify the contents of memory location to a particular value, not a given value, and it returns the old value. So as you can see here, once again, this is atomic, and we're going to go ahead and store, we're going to go ahead and set the location to 1. So that's all we're doing. It's like lock. And it'll return the old value. So it either returns 0 if it was unlocked, or it returns 1. In any case, we've set the value to 1. And you could also use test and set to implement a spin lock. And here's what it looks like. So this is lock and unlock. Whoops. So what's going to happen here is while this thing returns 1, you keep spinning. And then only if somebody had set it to be 0 will this thing return essentially 0, right? Even though it'll also have locked it. So test and set will automatically do the check in the same way. So the question therefore arises, why the heck would you choose one of these versus the other, right? So what's the difference between compare and swap versus test and set? Well, it turns out that compare and swap is a more general solution to this problem. And if you want to read all that you need to know about all this stuff, take a look at this link. It's got a really nice summary of many different low-level atomic locking operations. So the reason why compare and swap is the one that people bake into the hardware these days is because it's more generalized. Because you can set location to some arbitrary updated value rather than always setting it to 1. And the reason this is useful, as we'll see in a second, is that the various atomic classes in Java use this compare and swap capability in order to be able to do atomic counts that increment and decrement a value by some amount. Whereas test and set wouldn't allow you to do that. It wouldn't implement that at the hardware level. So the key thing to remember is that compare and swap is a more general solution. What are human-known uses of atomic operations? My favorite, again, because I like Star Trek, is the Star Trek transporter. And so that obviously converts a person or an object into an energy pattern, metaphorically speaking, since it's science fiction. And then it beams them to some destination and they're turned back into matter. And obviously, it better work atomically, right, if you stop halfway through, that's probably actually a plot from a bunch of Star Trek movies, but if you stop halfway through, horrible things will occur. And there's actually a Wikipedia link that talks about transporter accidents, right? So I'm sure that figured prominently in some of the shows. Okay, so that's basically the end of that part.